Okay. Um, okay. For the following questions, draw a diagram to explain your problem-solving process. Okay. Consider the worst possible insertion order for 10 strings, each 3 characters long to ternary search tree. Was the height of the tree after these insertions? Well, the worst possible scenario would be that none of those strings share this exact same prefix, and so what happens is that instead of, them, since a ternary search tree, stores characters instead of strings, which allows it so strings that share the same prefix don't always have to add to the actual height as much as it would. So 10 strings, each 3 characters long, what's going to happen is that, you're going to insert your first string, um, and then that's going to already have a height of 2. And then you're going to insert 9 more strings, and then assuming that they all, go to either the left or the right, all of them are going to add a height of 1. So it's going to be 11, and then that's shown here with just 10 3-character long strings. Okay. Consider the worst possible insertion order for 10 strings, each 3 characters long, into a binary search tree. Was the height of the tree after these insertions? Okay, so the worst possible case for a binary search tree is that it's gonna it's gonna have a linear height depending on the nodes as yeah, it's gonna have a linear height depending on nodes as opposed to a logarithmic height depending on the total amount of nodes it has. So in worst case scenario, it's essentially going to be linkless, and that happens when um again, like the insertion order is like either like, I don't know, greatest to least or least to greatest, and so again, it's just gonna be a worst case scenario. It's gonna be the height is gonna depend on the amount of nodes, and so there's gonna be 10 nodes, so it's gonna have a height of 9. But um, here it is again with the same exact strings, a to j j j j. Hmm. Um, okay. So for this left-leaning red black tree, was the height of the corresponding 2-3 tree. This can be found, either by gluing it back together to 2-3 tree by visualizing that, or you can just count the black nodes the black links. So that's just gonna have a height too. And at least how many values you need to add to the corresponding 2-3 tree in order to cause a height increase. Okay, so visualizing the 2-3 tree. Since 2-3 trees sort of grow upwards, and that it doesn't create new leaf nodes. It's going to overstuff its leaf nodes until those actually propagate up. And so what's going to happen is, if you're asking the minimum amount to cause a height increase, the root already is going to have 2 keys for this 2-3 tree. So what's going to happen is that you need to find some way to minimize, the amount of actual nodes you need to add for the nodes for a node to propagate up to the root. So this 2-3 tree is one of the leaf nodes already has 2 keys. So what you want to do is you want to start with the one that has 2 keys. So that way you're going to add one, and then that's going to propagate up to here. And then you just have to get this to propagate up. So it's sort of very helpful that one of these already has 2 keys. So it's going to be 3 because, if you think about it, you're going to add one here. That's going to propagate up. Now you're going to have 2 keys and then 3 nodes. And all you have to do is you have to add 2 more to one of those 3 nodes. And then that's going to propagate up into here. And then the middle one's going to propagate up. And then that's going to propagate up to the already 2 key root. And then that is going to split and increase the height of the tree after it creates a new root. So that's going to be 3. Okay, at most, how many values can you add to the corresponding 2-3 tree without causing a height increase? Okay, so visualizing the 2-3 tree again, what's going to happen is that don't as long you can keep adding items as long as one doesn't propagate up to the root. So what that means is that you can get these middle nodes here, or yeah, you can essentially get these like middle nodes here to get to a 2 keys, and then you can get all the leaf nodes to 2 keys. So what that means is that what's going to happen is that you're going to add 2 to one of these a bottom leaf node. That's going to propagate up. That's going to be a 2 key middle leaf node. Then you're going to have 3 three children of that middle leaf node. So you can add two to this one. You can add two to this one. That's going to be four. And then for each of those, you can add one more to all the child nodes, that being the leaf nodes, and then that's gonna be 10. So then, this leaf node already has two, so you can add one to it, make the middle one two, and then you can so that's 11, and then you could add three more, one to each of those children nodes, and then that's gonna stuff those with two, and then after that, obviously, anything that you add after that, that's going to cause one to propagate up to another, to propagate up to the root. So yeah, 14. And then at least how many values do you add to the left-leaning red-black tree in order to cause a height increase? Well, it would only be one, because, if you think about the corresponding 2-3 tree, all you would have to do is you have to add one to leaf node, and then, because all the left-leaning red-black tree does is it splits the nodes with two keys to make it a valid binary search tree. So, you add one, it's going to be, adding one to the leaf node, that's going to be a two-key leaf node, and then that's just going to split down to the left. So it would only have to be one after you convert the 2-3 tree to a left-leaning red-black tree. Okay, so what happens when a new element with a greater value than all the other elements is added to this left-leaning red-black tree? Well, if it's greater than, what's going to happen is that it's going to be all the way down to the right, so right over here. So, if this was a 2-3 tree, this would be a stuffed leaf node with two keys. So, so it would be inserted with a red link because, the red links correspond to the nodes that are going to have two keys in them. So it's going to have a red link. But what that means is that it is now violating, the whole point of the left-leaning red-black tree, and that being that all the red nodes are going to be to the left. So what you would have to do is you would have to rotate it to the left, so that way the red node is pointing to the left. So what's going to happen is that insert a red edge right leaf hanging off the rightmost branch to represent an element, and then rotate left on the leaf's parent node. So yeah.